All right. This is too loud. Can, can- like this? Like this? Okay, thank you. All right. First of all, welcome back. Thank you on this beautiful day for coming back. And welcome back to Frustration and Criticality in 2D Heisenberg Antiferromagnets. And today we're going to talk about frustration and how it can lead to emergent criticality. But let's first do a quick recap, because you've had many lectures and beaches in between since our last time. So is that big enough? Can you see that in the back? Good. Okay. Please let me know if you can't hear me or if you can't read anything. Hopefully you want to read and hear me. Okay. So we know very well that frustration can lead to disordered states. Okay, that's pretty obvious. And I'm talking about at finite temperature. So for example, states at finite temperatures, the canonical case is the Ising triangular lattice. We talked about that last time. Ising triangular lattice. At finite temperatures, defects are entropically favored, and so we have exponential spin correlations. I also remind you, and this is not a frustrated case, and this has been mentioned by many speakers. I think Jean-Noël, Piers, and André also mentioned it, and in fact, Lucille mentioned it this morning, that the 2D Heisenberg antiferromagnet, the Néel antiferromagnet, for example, on the square lattice, has at finite temperatures a finite stiffness, and as we talked about last time, it has a correlation length. Remember, we said that at t equals 0, it's ordered, so that means it goes as x of 1 over t. Then we know this has to be dimensionless, so we have a js squared, and then we do a lot of calculation, spin wave theory or Polyakov scaling, and we get the 2 pi. Okay? A lot can be done on dimensional analysis. So let's just talk about what the motivating question was last time. The motivating question was, can short wavelength fluctuations in a 2D Heisenberg antiferromagnet lead to long wavelength physics and order, okay, at finite temperatures? And what we found, I'm zooming close to the forbidden zone. So what we found was, that frustration in a very simple model can lead, and in our case, it was to a Z2 order parameter. How does this work? Well, frustration leads to a degenerate manifold. You have many states with the same energy, but these states do not have the same entropy, and so when you increase the temperature, the states with the maximum entropy are selected, and this goes by the term order by disorder. A number of you asked me whether there was any randomness involved. No, the disorder is the fact that we have a large ground state degenerate manifold, no long range order, but then we have classically fluctuations, thermal fluctuations that select states with the maximum entropy. And so what we have is that in the case that we studied, we have the ordering of relative spins, and we actually showed that we have a finite temperature Z2 transition. Okay? So that's what we did last time. So now we're gonna say we're greedy. Last time we showed that frustration led to a Z2 order parameter. Can we actually find a frustrated model that through this order by disorder mechanism leads to ZP, where P is greater or equal to 5. Now, why would we want to do that? Well, remember that Z2 is just up or down. I don't call it Ising because we don't break time reversal invariance, but it's up or down. This is a clock model. It would be, for example, if it's Z4, it would be 1, 2, 3, 4. It's a clock model, so you have to worry about the ordering. Okay? And why are we interested in this? Well, in 1977, in a beautiful paper, Jose, Nelson, Kadanoff, and Kirkpatrick showed that in a 2D nearest neighbor antiferromagnet of clock model, for p greater than 5, you can host a critical phase. Now remember, what does that mean? It means that we can have power law correlations. Did you have a question? No. Okay. It means we can have power law correlations. We talked a little bit about criticality last time. Remember, the beta showed that the spin half Heisenberg chain, 1D, is critical. Okay. Here what we're saying is that if we can get fluctuations to select, let's say, Z6 clock model, then possibly we could host a critical phase with algebraic with power law correlations. And so, oh, sorry. So it's a clock model. Sorry, thank you. Okay, it's a clock model, yes. And this is the Jose Kirkpatrick. Yeah, thank you. Good, you're paying attention. Great. Thanks, Lee. Okay, so this is how we can get from frustration to emergent. The question is, can we then get from frustration to emergent criticality? Now, you might say, wait a minute. Do we have an issue with Merman-Wagner? Okay, Merman-Wagner tells us we can have in a nearest neighbor model, we can have no symmetry breaking at finite temperatures, so we're good. Then you can say, wait a minute. Last week, we learned, and I think this was described in a couple of the previous lectures, Jean-Noël, and I think Piers mentioned it, and also André mentioned it, that in 2D Heisenberg antiferromagnets, let's just call them HAFM, we have homeotopically stable vortices, pi1 SO3, but they do not bind. We do not expect Kosterlitz-Thalès physics in Heisenberg systems because of the finite stiffness. Remember, we have a finite correlation length, and so we don't expect them to bind. So what am I talking about? Okay, in a Heisenberg, we don't expect Kosterlitz-Thalès physics in a 2D Heisenberg system. We do expect it in 2D XY system because there we don't have a finite stiffness. Okay. So what we are asking is the following, and that's going to motivate our discussion today. Can we identify an isotropic Heisenberg model with an emergent critical phase, even though it has a finite Heisenberg stiffness? And what we're asking is whether or not we can get power law correlations in the relative spins. So the approach is that we ask whether we can construct a model such that we have fluctuation selection of a Z6 phase, okay, a Z6 clock model, and then following the beautiful work by Jose et al., we're going to ask whether we can host a critical phase in a Heisenberg system. So that's the plan. Yes, André? We're going to talk about power law spin correlations, but it's relative spin correlations. It's not going to be a Heisenberg system, and I'm going to show you the model and everything. Yes. Well, you're going to see in the Z6 clock model, what happens is that at high temperatures, you have free spins. This is as a function of temperature. Then you have two BKT transitions. So you have a critical phase here. So you have two BKT transitions. And then you have a Z6. So this is temperature this way. Okay, so that's what I mean. All right, so what we're going to ask is, can we fluctuation select a Z6 clock model such that we can then flow into this? and I'll show you what some of the challenges involved are. Okay, so that's the plan. And could I have, please, so now I'm going to break all the rules. And because I have a time constraint because we have this public lecture and I can't draw very fast, and these involve lattices that I can't draw, I'm going to use slides. Okay? So excuse me. Should I turn off this light? All right. I should also say that part of my choice for this was coming from the students who I've enjoyed interacting with, and I look forward to interacting more this week. There were 2 questions that came up after the last time. Are we on? Yeah. One question was, okay, I gave a sort of impressionistic landscape of frustration. We talked about selection of discrete order, but what kinds of work is going on now? And the second question related to an interesting discussion that I overheard and then joined about why is it that we have to learn about topics that we're not directly interested in graduate school. And you'll see how they connect, because I'm going to show you a very unexpected connection that made me glad that I had to take some courses that I didn't necessarily want to in graduate school. Okay, so that's the plan. By the way, I'm glad not to be writing anymore. Actually, lecturing, it hurts your hand. How many of you have seen, you'll see how this is related, how many of you have seen the movie Gladiator with Russell Crowe? It's a great movie, right? And Russell Crowe does all his own stunts. Guess what? When he was in A Beautiful Mind and played John Nash, he got someone else to write at the blackboard. It was a math professor from Columbia, because he said he wasn't used to writing on the blackboard, and they found someone who matched his hand. So, with that, I continue on the slides. Okay. All right. So, the system we're going to look at is, and I should say by definition that this has a strong personal flavor, and I'm happy to share all of this, but it's an unabashed personal flavor to all of this, okay? All right, so the system we're going to look at is oops, this isn't even on, very good. The system, you can tell I'm a theorist. The system that we're going to look at, if we ever get this on, I hope it hasn't burnt out. Doesn't seem to be working. Okay, the system that I want to look at, I think it's gone. Oh, here, good. The system that I want to look at is a triangle and honeycomb system. You remember that last time we talked about 2 square lattices, a J1, J2 model on the square lattice. A square lattice is its own dual, and so we basically had a square lattice and its dual, also the square lattice. Now what we're going to do is look at a triangular lattice and its dual, the honeycomb lattice. We're all nearest neighbor antiferromagnetic, and you'll notice that on the triangular lattice, the ground state is a Néel state that has spins at 120 degrees. And in the honeycomb lattice, we have spins that are what we call uniaxial. They're up or down, okay? And the key point, as in the J1, J2 model, is notice that the local fields on this blue spin add up to 0, and that the local spins on this red spin add up to 0, okay? So we have a very similar situation that we had last time, that classically, okay, these 2 lattices are completely disconnected, okay? And what I haven't drawn here is from every blue to a red, there's a bond, okay? All right? Okay, so what we have is we have a Hamiltonian that looks like this, okay? And we're going to assume that the bonds connecting the 2 lattices are very small, okay? Just as we did before. So, classically, we have 2 decoupled lattices. Our order parameter is an SO3. SO3 is the triad, okay? That's from the triangular lattice, okay? And the O3 over O2 is the fact that we have the honeycomb lattice is a vector that can point in any direction, okay? Now, what are we after in all this? First of all, we know that order from disorder will drive coplanarity. Remember before, we talked about the fact that in order from disorder, the spins like to align themselves with the fluctuation perpendicular to the fluctuation vice field. So let's look at this triangular lattice. The fluctuation vice field, these spins are all in the plane, and the fluctuation vice field will always be parallel to these spins. And that tells us then that the honeycomb lattice, for order from disorder, we expect the honeycomb lattice to have its spins in the plane, so coplanarity. At the beginning, there was no reason for that because they were completely independent, but we expect that fluctuations, that thermal fluctuations, will select those states. So let's see what happens. First of all, let's just, before I start giving you a flavor of some of the calculation, let's just go over what we're after, okay? So let me show you what we're after, and then we're going to get there. So remember the J1, J2 model that we studied on the square lattice. At high temperatures, we have, this is a function of temperature, at high temperatures we have free moments. Then we have decoupled sublattices, and in this case we found that at a particular temperature, okay, the sublattice is locked, and we broke lattice symmetry. We had ferromagnetism in one direction or ferromagnetism in the other, and that was our Z2 order, okay? And that went all the way down. Now, what are we after here? We're after something very similar, okay? At high temperatures, we expect, let's go back a minute. At high temperatures, we have decoupled sublattices. Then we're going to have coplanarity. But here, the idea is that can we get, and we'll find that we do, a critical phase, and then at low temperatures we get a 6-state clock model. Okay, so that's what we're after. Okay, so first of all, how do we get the coplanarity? And then we'll divide into 2 bits. To get the coplanarity, we actually have to do spin wave theory. We talked about spin wave theory, and today Lucille talked about Holstein-Primakov. That's how we have to do it. We have to roll up our sleeves and do a calculation. When we do that, we find that we have coplanar ordering. The minimum occurs at theta equals pi over 2, and we have 6 degenerate minima in the plane. So what we find is we have the following action. We have what we're interested in. We've talked about spin waves. We're interested in the small variations of the spins. This is reflected in a gradient like this. Okay, so we have a gradient. This is the honeycomb lattice. This is our triangular lattice. We don't have any cross gradient terms because they don't respect the point symmetry and time reversal invariance of the system. And now let's look at the terms that couple. The terms that couple the 2 lattices, we have a cosine squared term. This is our term that makes us, a potential term that makes us go collinear. That's the gamma here. And then we have another term, which is our 6-fold degeneracy. Both terms are relevant at high temperatures, okay? What we do on this, and I just give you a flavor here, is we do a renormalization group calculation. And what we find as we go to larger and larger lengths is that the stiffnesses here get smaller, but this potential term here gets larger and larger. And when it becomes of order 1, that gives us a length scale, okay? And that length scale is very similar to the length scale we got last time for the domain wall width. And in fact, in order to get the coplanarity crossover temperature, we compare the coherence length of the shortest coherence length associated with either the triangular or the honeycomb lattice, and we compare it with the length that we get, which goes like J1 over J2, and we find that the coplanarity transition has this form. It's very similar to what we got before. Okay, so we started off with an SO3 order parameter O3 cross O2, but now what we have is we have an SO3, but now we have a U1 order parameter. Okay, our honeycomb lattice is completely in the plane. But let me remind you that this is not good enough. Unless we decouple that U1 degree of freedom, we have no transfer critical phase. because if in a Heisenberg system, we'll have a finite stiffness and we will not have binding. We have to show, in order for this to work, we have to show that our U1 degree of freedom decouples. So how do we go about doing this? Well, we have to do scaling in the coplanar state. We have an order parameter. So here's our coplanar state. We have our SO3 order parameter, and we have U1. You can think of it as the SO3 being a center of mass motion of the underlying spin fluid, and the U1 being like a relative phase between the two sublattices. This action is no more than just looking at the kind of action you learn about in classical mechanics. This is like a top with moments of inertia. This is SO3. This is our U1. But this is the nasty term. This is the term that couples the U1 and the SO3 degree of freedom. So how do we go about doing this? We want to show that we have decoupling of the U1 degree of freedom with a finite XY stiffness. Now, the conventional way in antiferromagnetism is to use what's called the Wilson-Primakov approach. In the Wilson-Primakov approach, not Primakov, Wilson-Polyakov approach, sorry, or Holstein-Primakov is spin wave theory, Wilson-Polyakov approach. And what do we do here? Well, it's very similar to what Jean-Noël talked about with fast and slow degrees of freedom. What we do is we assume that the longitudinal degrees of freedom of the spin are slow and the transverse are fast, okay? And we consider the fast degrees of freedom, and the spin amplitude is fixed. We consider the fast degrees of freedom up to Gaussian order, then integrate them out and rescale the action. And we watch to see how the stiffnesses flow, and in particular what this term does, that's what we're interested in, as a function as we go to larger and larger lengths. It's called in the literature poor man scaling by Anderson. He did this with the Kondo model. I guess in my case it's poor woman scaling. But anyway, that's what you do. And I have to tell you that for this system, it's pretty messy, okay? Because we have a lot of stiffnesses, there's a lot of bookkeeping, a lot of accounting, and you have to watch all your constants, all your minus signs, all of this. Okay, yes? Oh, it should be 2 and 3, sorry. Okay. Sorry about that. Thanks. Yes, so I have 3 Euler angles. You're completely right, sorry about that. I have 3 Euler angles, and actually this is gonna come up in a minute. I have 4 Euler angles altogether. 3 associated with SO3 and 1 associated with that. And I wish I could say that I put that in so to make sure someone was paying attention, but it was a mistake. Sorry, thank you. And please, ask questions and all of this. I make lots of mistakes. And that's one of the reasons that doing this kind of calculation is painful for me, because if there's a chance of me making an algebraic mistake, it will happen, okay? And this is important. Yes?
Also, can you explain why there's a sign difference between the first term and the second term? Because I've noticed that you...
This doesn't have a sign difference. What is the issue? Oh, that's a typo. Again, sorry. There shouldn't be a minus sign. There should be a plus sign.
Cool.
Okay? Another typo. Sorry. You're completely right. This is basically like a top with 4 Euler angles and a couplet term. Okay? And you can see why I need another approach, because I can't even write down the action without minus sign problems and all of that. Okay. Now let me tell you about the conversation. Actually, Miska was part of this, and others that came up. There was a group talking about why do we always have to take these courses, and in particular, they were talking about general relativity. Well, when I was a graduate student, I had to take general relativity too, and believe me, in those days, we had to wade through indices. There were no Mathematica codes. I realize you can't believe you, but we had to wade through indices, and it was serious bookkeeping. Well, it turns out, believe it or not, that in this problem, that helps a lot, and let me explain why. And by the way, this is not going to be just a cute analogy. This is actually going to be conservation of tedium and conservation of mistakes. Mathematica is going to do all the work. So let me tell you how this works. We have, as Misko pointed out, we have a magnetization that's basically a four Euler angles, okay? So we can think of our magnetization as a 4D vector, okay? Now, we can think of our action then as we're interested in understanding spin configurations, right? And we can map those 2D spin configurations of our system with 4 Euler angles onto a string that's moving on a 4-dimensional manifold, an S3 cross S1 manifold, okay? And if we do that, our long wavelength action, so this will be our target space, our 4-dimensional manifold. If we do that, our long wavelength action is a 4D string theory, okay? And if you want to be fancy, you can say it's a Euclidean version of a Nambu-Goto string. This is baby string theory. 4D is baby string theory. Okay, now, why do we want to do this? Is this something just cute or what? Well, Dan Friedan, who's actually our colleague at Rutgers, he showed that you could treat the nonlinear sigma models of antiferromagnets in this fashion, taking advantage of the covariance of the action. If we make coordinate transformations in target space, the scaling equations have to be invariant, okay? Now here, the spin stiffness that we got from spin wave theory, Holstein-Primakov theory, gives us the metric tensor, okay? So we input the metric tensor is our spin wave stiffnesses, which we've calculated, but remember, we want to know how those stiffnesses scale, okay? That's the whole idea. And so what Friedan showed is that, given the constraints of the problem, if we're interested in seeing how the metric transforms, that's going to tell us how our spin stiffnesses transform. And you can show that it's related to this Riemann tensor, Ricci flow, which is related to the Christoffel symbols. And our friend Dan Friedan, kindly, with conformal field theory, has calculated that minus 4 pi. In fact, you can even go to 2 loops and get the next term, which is to do with the Riemann curvature. Now, what this is telling us is that the Ricci flow of this 4-dimensional string theory is going to tell us about the renormalization of our spin stiffnesses. And so what we can show is that the decoupling occurs, and let me just give you a flavor for that. We write down this scaling thing. I'm sorry, the signs are still wrong. We write it like this. We write down our spin wave stiffness. We use Mathematica, full simplify, and guess who does all the work in this Mathematica? What's crucial here is that you can actually do a coordinate transformation. You do need some human intervention here. The decoupling becomes complete. You get the scaling equations, and as the isotropy develops, we can show that the U1 phase decouples with a finite stiffness. So we have the decoupling of the U1 degrees of freedom in 2 distinct parameter regimes. That's all that we can do the calculation. When the triangular J is much larger than the honeycomb one, and vice versa, that's all that we can do analytically. And amazingly enough, doing it this way gives the identical results as doing it with the Wilson-Polyakov approach. Okay. But thanks to Mathematica, we input the spin wave stiffnesses in terms of the metric tensor. It gives us the Christoffel symbols, no wading through all the indices like what I had to do. So that's fun. So let's go back. So what we have is we have a toy compactification problem. What turns out here is we have SO3 cross U1, but what we find is that the dimensions, the SO3 stiffnesses, they curl up, and we end up with a sort of ring world of U1, and then we flow straight into this phase diagram. So we are able to show that we get a BKT transition. The vortices, the way we calculate that transition is the core size of the vortex are actually the coplanar length that we determined before. You can calculate the BKT transition. It has to be below the transition where the U1 degree of freedom spins off. And then at lower temperatures, the Z6, the clock model, kicks in, and we get 6-day clock model. Did you have a question? Oh, okay. Any questions? Yes? It's by construction. Yeah, but we have, it starts with a 6-fold symmetry. We have a honeycomb and we have a triangle. In this case, what we find is when we have coplanarity, the fluctuations select, we had two potential terms there. One was gave us the coplanarity, the other one gave us the 6-fold minima. Okay, and that's due to the construction. And a honeycomb, yes. It's by construction. And we were going for the 6-fold symmetry because we knew about the Jose work. Okay. So, pardon? Yes. No, which I don't think I'm doing anything with Polchinski. So we did both, the Wilson-Polyakov, the Wilson-Polyakov, and then we did this Friedan coordinate geometry. Yeah. It's weak coupling, yeah. Yeah, well, that's why we have to do numerics to check on this. That's exactly what I was going to get to. So there are two things. First of all, as we just heard, this is all weak coupling. Second of all, we can only do the calculations in certain limits. And third of all, we assumed there were second order transitions, and there could be nasty first order transitions that crop up at any time. And our treatment did not do that. So then we went and did numerics. And when we did a quote unquote computational experiment, just to show you, we actually saw that there was an XY critical phase. We were XY disordered, XY critical Z6. So that confirmed everything. And in fact, one can show that there's a data collapse with the BKT scaling ansatz. So we really did have a critical phase. Okay, so of course the question is, can we connect with experiment? That's a bit rough, I should say. There is some talk about looking at chromium on a triangular lattice, but we're still a ways. We would have to have a bilayer, a possible candidate for a power law phase. That's still a long way away. Of course, cold atoms are wonderful because one can design all kinds of interactions, but mostly they're experimental realizations of XY systems. So the question is, what would happen in an XY model? We're currently working with a student to try and understand an old problem in liquid crystals. This would be an XY problem. Here, one might have a fluctuation-induced Potts transition, but the complication there, of course, is that you have free vortices above the BKT transition. Okay, so that's a little bit far from all of this. All right, so now let me give you a flavor for some other work that one can do. Everything we've talked about has been for entropically selected states. But one of the questions that crops up is, does such fluctuation-induced symmetry breaking occur in 1D quantum spin models? In other words, is there a T = 0, 1 + 1 analogy of this kind of 2D classical phenomena. And this is work done in progress with Pierce, with Peter Orth, and with Shivaji Sondhi. And one of the questions we asked was, let's see if we can get an emergent Z2 order. But what we're really after, I should say, is an emergent critical phase in a quantum system, an emergent Luttinger phase. That would be great. But we're not there yet. But let me tell you where we're going. We have a 1D J1, J2 model. And the first thing you might think, we take this and we wrap it around ourselves like this. It's infinite length along the y, finite length along x. It's periodic boundary conditions. And we get a spin wave dispersion of this sort. So we're finite in the x direction. But when we do our spin wave theory, we only get one minimum. It's ferromagnetic along x and antiferromagnetic along y. And we realize right away that the tube geometry breaks the symmetry between the J1 bonds, okay? So this won't work. But as a brief experimental aside, I should say that one does see pressure-induced superconductivity in one of the iron-based ladder materials related to the materials that Amalia talked about today. And interesting enough, even though there's emergent Z2 order in the bulk pnictides, in this system there isn't. It's antiferromagnetic along the legs and ferromagnetic along the rungs. Okay, but back to our issue. What if we rotate it by 45 degrees? We can get the symmetry restored between the bonds. We have a T equals 0 fluctuation energy, and sure enough, we have 2 minimum. So what we have is, we have a picture like this. You can see why I needed slides. I could have never drawn this. Picture like this. And we have distinct chiralities of the twist of the ferromagnetic spins around the nanotube. And what we also find is that it seems to be the case for L greater or equal to 2. L being how many across do we have. And that's good news because then we can do some analytic calculations. Okay, so what we have here is we have a quantum J1, J2 spin nanotube, okay, with 2 fluctuation selected minima, and they correspond to right and left chirality. This is sort of a quantum analog of what we were discussing last time, okay? But now you can say, what's the phase diagram of this beast? Well, what we can do is have an argument similar to what we did before. We have to calculate the correlation length. Now we do so using a technique called Schwinger bosons, which is a sort of generalization of Holstein-Primakov. Okay, we get a correlation length. Now you notice that we're quantum. Before we had a JS squared over T. Now we have no temperature, but we have an exponential of S, and then we have some other terms, okay? We have a domain wall width like last time, and so we have a domain wall width between right and left chiralities, and what we find is that now, remember, we're not going to get a transition temperature, but we're going to get a critical S, okay? And so now we can calculate our critical S, and actually when you do this with Schwinger bosons, you get something very similar to all of this. And so the kind of phase diagram we expect is J1 over J2, 1 over S. We have Z2 chiral order. We have a disordered state. And remember, we never have long-range order, so we have short-range nail order. And as we go across here, we have a gap. It will be gap full here, gap full there, but we'll have a quantum critical point. Okay? Now, there are a number of questions that crop up. What's the nature of the gap? What are the quantum numbers of the excitations? Now, the Z2 degree of freedom is just a scalar, so you can say, well, why do I care? But what about domain walls? Could they carry some quantum numbers? You may have heard of the Sushri-Verheeger model, where you have dimerization, okay, alternating, and there the domain walls actually carry quantum numbers. Could we have something like that here? Okay, we could think of a soliton. That's what happens in the Sushri-Verheeger model. Could we have some interesting behavior with these domain walls? Do they move? Do they have quantum numbers? That's something we're still working on. Okay. And the other point is what happens with L odd versus L even. We know that in ladder compounds, L odd and L even are quite different. Okay? And so the question is, do we have that situation here? Everything we've done has basically been done for L equals 2 or even, basically. Okay. So what we have here is an emergent Z2 order parameter in a 1+1 Heisenberg system. How would we confirm this? Well, their matrix product, this seems very, it would be very fruitful to study this with a matrix product representation. And what about experiment? It's not yet, but optimistic. In 4-leg antiferromagnetic Heisenberg spin tubes, people have measured excitations. Okay, this is so complicated that even the physical chemists have names, Scool copper chloride. But now let's ask the real question that we're after. Can we get a quantum analog of this critical phase? Okay, that's what we really want. And this is all question mark, because I promised that I would talk about things that are in the future. What we would expect as our phase diagram would be some sort of Z6 order, but now we would have an emergent Luttinger liquid, a disordered phase, and so as we came across here, instead of having a critical point, as we do in the model that we're studying, we would have a critical phase, okay? And that would be very interesting because it would mean that we have an emergent Luttinger liquid, basically fluctuation selected, okay? But that's still something we're working on, a fluctuation selected criticality and a 1+1 integer S. Heisenberg system, stay tuned. Okay, so I think I'm pretty much ending. Okay, so let me just go back for a minute. Oops. So let me give a summary. We've talked about order from disorder, the fact that when we have frustration, a hallmark of frustrated systems is the fact that we have large ground state degeneracy, fluctuations, thermal or quantum, select states, usually ordered from this degenerate manifold, and we call this order from disorder. We talked last time about experimental confirmation, okay? In particular in erbium titanate, and Lucille and Leon, who worked on that, are here if you have questions about it, okay? And so order by disorder has been confirmed in systems, okay, experimentally. Now, what we talked about also was finite temperature, Z2 order parameter, okay? You can have other clock order parameters that are fluctuation selected. In particular, we talked today about a Z6 order parameter that was fluctuation selected, and how we got emergent criticality in 2D frustrated Heisenberg systems. Now remember that the Heisenberg correlation length in all of this is finite. What we're talking about when we're talking about emergent order parameter and emergent criticality are relative spins, okay? So we have long-range order in these discrete order parameters, and we have power law correlations in a relative spins. We've talked about application of Friedan scaling to magnetism, connecting this to sort of other areas. This is a realization of mapping of renormalization group into time, which is now very popular in the ADS-CFT community. We mapped our renormalization group equations onto a string moving in time on a 4D manifold, 4D because of the Euler angles, okay? And we also asked the question, what is the quantum version of this? Can we suppress this Z6 all the way down and get a power law, some sort of spin liquid? We haven't been able to do that, but that keeps us busy. As Giovanni said, we're not We have lots to do. And now, let me be a bit fantastical, okay? You may have heard of Perelman's proof of the Poincare conjecture. How many have heard of that? Okay? And here I'm talking completely out of my comfort zone, okay? Poincare conjecture, if I understand right, and others may be able to correct me, is in 4D tells us that every simply connected manifold should be homomorphic to a 3-sphere. Is that correct, Mark? I think that's right. Yeah. And Perelman, using something called the Hamilton program, was able to solve this problem using Ricci flow. And as I understand it, what he did was he basically did surgery. There were some singularities, nasty singularities, and he did surgery on that, and he was able to then prove the Poincare conjecture. Now, what we found was that we had a 2D antiferromagnet where we could write down the action and we could consider the spin configurations as a string in one space dimension, one time dimension on a 4D manifold. And what we found was that the Ricci flow was a way of understanding the renormalization of those spin stiffnesses. The question is, could we run this backwards? Okay? If we're to take this connection between 2D antiferromagnets and Ricci flow seriously, we would say, from a stat-mech standpoint, that the singularities that occurred before in the 2-loop Ricci flow are what we call false Landau poles. It means that you stopped the beta function too early. There are relevant terms beyond that, okay? So one crazy idea, and it's important to have crazy ideas at all ages, is could we actually come up with classical magnets to simulate the Ricci flow of the manifolds that the mathematicians are interested in? Okay, so the particular antiferromagnet that we did is too simple for them. It has what's called a homogeneous metric. That means that basically the metric is everywhere the same on the manifold. You would need something more complicated. Their manifolds are much more complicated than this. But what would be the protocol? You'd find a suitable magnet that realizes the given metric. That means the spin wave stiffnesses, you have to engineer them so that they have the right way. You cool the system. You'd measure the spin correlation functions at various temperatures. You'd extract the metric tensor, and then perhaps you could obtain a surgery-free generalized Ricci flow. So it may be that by doing that, you could actually come up with some sort of proof of the Poincare conjecture without having to do the surgery. So I can't make too many links with experiment with all of this, but there was an unexpected link with gravity, and I, for one, am glad that I had to take a course in general relativity. So anyway, that's basically it. I'll open the thing for the session for questions, and I look forward to discussing any of these issues and more with you in the next week. Okay, thank you. Do I have any questions? Yes?
So I think what you taught today has a very steep learning curve. But can you give us a little more motivation or about this RT program that you're using?
Which?
Is it equivalent to the Wilson Coleman?
Yes. Yes.
So through this, I guess through this method, you can get more intuition, or?
No, it's basically you get Mathematica to do the work. Well, Piers, you want to comment? You look ready to comment on that. No, the point is the following. The Wilson Polyakov renormalization group is beautiful, but particularly for this system where you have lots of different stiffnesses, it's a lot of work. because you have to keep track of everything. Here, once you've calculated the spin stiffnesses, you can put them into, and you know the Christoffel symbol, you can calculate the Riemann tensor and everything. You can actually then just have Mathematica do all the work. So it's much simpler, thanks to Mathematica. Do you have any comments on that, Piers? Yes. Okay. Oh, but we got exactly the same results. That's the beauty of it. And in fact, we joked with Dan for Dan that we checked his minus 1 over 2 pi, which he got from some beautiful conformal field theory. But when we did the Wilson-Polyakov and we did this, we converged on exactly the same point. So it depends. In this particular case, it's, you know, it makes it much easier. Okay, so thank you, everyone. I think we have to get ready for the public lecture, and I look forward to, oh, did you have a question, Mark? No. You're giving the public lecture. Okay, thank you again.